So, hello, my name is Michael, and I would like to welcome you all to the first PoreLab lecture series session this autumn semester. And from now on, we will extend our format a little bit and will also stream each lecture live on YouTube. And therefore, first, some words about the lecture series organized by PoreLab. The lecture series started in 2017 and is a weekly lecture given by experts in the field of porous medias. The topics are widespread and can cover pretty much everything which is related to porous media. Over the years, we've heard quite some interesting talk, and we would like now to share that pleasure and make these talks more accessible for a broader audience, which is why we decided to also now stream each lecture live on YouTube. The lectures will be given at each Wednesday at 1 p.m. and there are now then 3 ways of joining. One is live at PoreLab, the other is via Zoom or YouTube. Yes, and if you have questions, just raise your hands or post them as a comment in the chat. So, but now to the most important thing of this lecture today, that is our guest. I would like to welcome Federico Municchi. I hope I pronounced the name correctly. He's a research fellow in applied mathematics at the University of Nottingham. He did his PhD at the University of Graz in Austria and worked there on coarse-grained models to describe the momentum, heat and mass transfer in dense particle suspensions. And today he's going to talk about multiscale modeling of transport in heterogeneous reactive media. And here he is in particular discussing the methods of a recent publication with focus on the computational aspect. Yeah, I would like to give the word to Federico.
Thank you very much for the nice introduction. I do want to share my screen. And, great. So I suppose now you can see my screen.
Yep.
Great. Okay. So, well, I don't need an introduction anymore, so we can jump straight into the presentation. So it will be about multiscale modeling of transport into heterogeneous reactive media. Special focus on conjugate transfer and surface reaction. Now, in our group, we actually work in porous media from many points of view. We attack many different perspectives. For example, we have some working in power mechanics. We are also combining porous media and batteries. And we are using OpenFOAM a lot, which is an open source finite volume library. We have a lot of solvers implemented there, a lot of applications that can be used to solve many problems in porous media. For example, variable density Darcy flows or power mechanics, specifically power elasticity. Anyway, today I will talk more about the theoretical models and their implementation also. So first of all, a concept that is very fuzzy often, but that's actually crucial for our analysis, that of a representative elementary volume. So if you consider this as a kind of porous column, so here we have a porous medium, here we have a flow entering, flow leaving. So this part inside is heterogeneous, a heterogeneous medium. We want to perform our analysis in what is called this representative elementary volume, what it is. Well, first we identify an area that is sufficiently far from the boundaries so that boundary effects can be neglected. We define a macroscopic length L, which is normally a fraction of the length of the macroscopic device or the reservoir we want to study. It's a length of interest at which we want to describe our problem. The REV is defined based on another length, small l, which is it's calculated in a quite a fuzzy way. Imagine we are averaging larger and larger regions of this porous medium. We'll see that the microscopic fields, for example, concentration of a contaminant, velocity field, or porosity, are oscillating a lot when the volumes taken for averaging are very small. And then at some point, they don't oscillate at all. They just follow some macroscopic heterogeneity. For example, if the overall porosity varies from 0.5 to 0.3, to say, then that would imagine that it's linear, for example, then this linear behavior is what we will see in the macroscopic heterogeneity region. So the REV is defined as a kind of cutoff where we don't have any more statistical oscillations. In some particular domains, in some particular media, it's very easy to define REV. For example, if the domain is periodic, we have a self-repeating geometry, then the REV is the unit cell that is repeated. That's quite simple. So examples can be the one on the left. That's exactly a self-repeating cell, even if it is very complicated. We have a concentration field or a temperature field or whatever scalar you may be interested in analyzing. And you see that this field is varying over the length of this medium. At some point, it's saturated. It gets to 1, the maximum. It doesn't exchange anymore. So if you use a standard, let's say, volume averaging approach, and you want to evaluate the Sherwood number, which is the dimensionless transfer coefficient between the grains and the fluids, you will end up in trouble. Similarly, you can have geometries that do not represent a representative elementary volume. This is quite similar to the example geometry I showed before in the drawing, to some extent. And of course, if you take a region here in the middle, this can be considered a kind of representative elementary volume, because you see there is a repetition. Even in reality there is no repetition, they are randomly distributed. But here it looks like the field is quite the same. Still, you have the same problem. You have the same gradient of the field. Clearly, the analysis does not apply here because we have a very strong transition from porous medium to not porous medium. So, talking about inhomogeneous surface reactions, now we'll describe in detail what I mean by inhomogeneous surface reactions. I will refer to a paper we recently published in Advances in Water Resources. So all the details are there. I will explain the methodology we employed. So imagine that this is your porous medium. You have some grains. From the introduction, you understand I come from particular flow, so I like to represent porous medium as a collection of spheres with different grains. It's easier, at least for this kind of drawing. And imagine that we have reactions at the surface between at the interface between these grains and the fluid that is flowing. And the scalar in this fluid obeys this PD, which is classic transport equation, backchain diffusion. And we have Robin boundary conditions at the interface because we have a reaction. And they are inhomogeneous, so we have an additional flux. So these are often called internal boundary conditions because when we perform volume averaging or to scale asymptotics or whatever technique, we want to get rid of these boundary conditions. In the macroscopic model, we don't want to solve them explicitly, clearly, otherwise it would be pointless. These are different from the external boundary conditions. That's why we said we are quite far from the boundaries, because we don't want to consider those external boundary conditions. And these, like assuming the dynamics of the smallest scales is described somehow just using local information. That's a very important point. For example, we have a flow with a very strong advection that can be difficult to justify. So now we have to make this equation dimensionless. We can choose two reference lines. One is L and one is big L, small L and big L. But does it make any difference? If you use small L, we obtain a dimensionless group, two-dimensional group, the Damkoller number, the packet number, and this is how the equation looks like, fine. But you would like to scale it with respect to big L, because we are interested in the macroscopic model. And so you see that these epsilons, which are just the ratio between the small L and big L, appear here in front of the packlet and from the Damkoller. This is a very important information because it tells us how the equations are scaling. So how the terms in the equation are scaling. So if we let this becoming very small, these terms will become very high. So clearly we are interested in L because big L reveals this scaling behavior. So how can we proceed? Well, we can use two-scale asymptotics. So two-scale asymptotics means that I define a fast scale Y, so a scale This is the coordinate of the scale L, let's say. So a derivative will be a derivative with respect to x, that scales with big L, a derivative with respect to y, that scales with small l. And then we express C as regular asymptotic expansion in this epsilon. Then we collect terms of the same order, no problem here, except that if we do this at the interfaces, so the boundary conditions, we see that the boundary condition for the lowest order implies that the leading order of our expansion is still a function of the fast coordinate y. Now it should be yxt to be precise. But this is not one, because being still a function of fast coordinate means that we are not able to describe the evolution of C0 using a macroscopic equation. We still need to account for the fast scale. So how did we attack this problem? Well, in a way similar to what has been done before, to be honest, by Allaire and Raphael. We decomposed the field C, but we decomposed it in a slightly different way, because the work was concerned with homogeneous Robin boundary conditions. Our extension was to inhomogeneous Robin boundary conditions. So what we did was this kind of decomposition. So C is equal to psi, just function of y, because we assume that G is a function of y, plus this phi, function of y, phi omega. So the objective will be to use psi to absorb the inhomogeneous part of the boundary condition, phi to absorb the homogeneous Robin boundary condition, and omega finally will be the field we want to upscale using two-scale asymptotics and volume averaging. And this should satisfy a Neumann boundary condition, an homogeneous Neumann boundary condition on gamma on the interface, so that we can upscale it easily. So the first step is the composition in psi. And we identified this problem for psi, since psi does not depend on time, does not depend on x. L is the advection diffusion operator. We just have this problem here that we have to solve at the level of the REV. Now, what is the advantage? The advantage is that this psi does not depend on time. That's it. So we calculate beforehand, and we have something that is independent of the dynamics of the system. If we look at the solvability condition, so basically integrating the equation of the boundary condition and checking that they match in layman words, we see that this is consistent if the integral of the surface of psi is equal to the integral of the surface of the interface, G. But in the end, we'll just need the average of psi, because we will perform volume average. So in some cases, we can already guess the value of psi. In the easiest case, where G is a constant, then psi is equal to G. You will see that in the final macroscopic equation, this will become very, very familiar, this additional term that arrives. So for phi, instead, we take another way. We take phi to be a positive eigenfunction. This exists thanks to the theorem of Klein-Gutmann. And this phi should satisfy the eigenvalue problem, which is this problem here, with this scaling epsilon -2, because L is only the part of the operator on y, because phi is only a function of y, not a function of x. And this takes the Robin boundary condition. And we end up with this problem for omega. Unfortunately, there is a big issue here, that there is this additional term that we want to get rid of. Plus, the velocity inside the advection diffusion operator could also be non-divergence free, and that could create some troubles with scaling. So a further modification we will perform later is well, here you can see that lambda actually, it's lambda here, the eigenvalue, is simply the Sherwood number. In the end, it's an equivalent of the Sherwood number. The difference is that here the problem is not time dependent, it's a steady problem. So we can calculate this very easily, just once and for all. We don't need to wait for the system to get statistical steady state, because we are already in the asymptotic regime. So going back to this equation here, the next step is introducing another field, which is the adjoint field. The adjoint field satisfies the adjoint equation, which is simply given by the adjoint operator. And we can consider that L omega, sorry, L omega is an operator itself acting on the field phi. What we do is just projecting this operator in phi dagger, so the eigenfunction, so in the space of phi, in other words. Remember that in the end we will average over the volume, and therefore this is really kind of projection. What we obtain is a modified operator that actually has all the properties we want. We have a new diffusion coefficient, we have a new velocity. This new velocity is very good because it's divergence free. Even if the starting velocity is not divergence free, this is divergence free. And this is the final equation, which looks very good. Why? Because now we can absorb this term here inside the time derivative and totally get rid of this additional term. In fact, this will be the next step, performing two-scale asymptotic with drift, as it's called. So this is the kind of transformation on omega that we have to perform. So drifting omega, Galilean transformation, using this velocity u star that we will compute later. And this reactive term that absorbs the reaction. And we collect the terms. So collecting the terms, we see that also the internal boundary condition expanded doesn't create any trouble, because at the lowest order, we have this problem here that is solved with a trivial solution of omega 0 that does not depend on y, which means that the method actually works. We can get a leading order that does not depend on the microscaling. So at the first order, at least the -1 order, let's say, the -1 order, we obtain a set of equations that can be solved, a Cauchy problem, so it can be solved using these ansatz. So we can express W1 as a function of the gradient of max of W0, multiply scalarly, scalar product with another vector, which is called the corrector. When we substitute this back, we obtain the corrector problem, the cell problem sometimes it is called, the first corrector problem. So this is another problem we have to solve at the REV. And we can also evaluate this U star, this big U star, so the velocity that we use for the drift. This is the macroscopic velocity actually. And we see something very important. The macroscopic velocity is not the average velocity based on the solution of the RC equation, but it's another kind of velocity. It's an effective velocity. It's also affected by the reaction rate. And the velocity is defined in the usual way. So at the leading order, let's say the order 1, finally we find an equation that then we can integrate to obtain the macroscopic equation. We just take volume averaging, and we obtain this big, huge term here. It is simply the effective diffusivity tensor, an effective dispersion. Now, substituting everything back, considering that the average of C is actually all these things here, we obtain the final form of the macroscopic equation. And you see, it's very familiar. Now, this packlet over epsilon is simply the packlet evaluated with the big L, packlet at the macro scale, which is what we would like to use, basically, the packlet relative to the macroscopic geometry. And we also have this reactive term, and you see we also have this this additional term that it's very similar to what the initial Robin boundary condition looks like. Expression for the effective diffusivity and effective velocity. So we have everything we need. Now the problem is that we ended up with a lot of sub-problems to solve. We have an auxiliary problem for psi, we have an eigenvalue problem for phi, a joint problem for phi dagger, and a cell corrector problem for chi. Finally, if we solve all of them, we can put all these parameters inside our macroscopic equation and solve everything. Luckily, we have a solver that does this kind of things. We implemented the solver in OpenFOAM, as I mentioned earlier. So this allows us to calculate all the parameters for the cell problem. So the eigenvalue, the effective diffusivity, and the effective velocity. And we also verified in this geometry here. So these are self-repeating cells. These are called FCCs. And we just compare the direct numerical simulation of this. You can see that the concentration is varying a lot here. And we compare this against the prediction from a one-dimensional model, this two-dimensional. It's a one-dimensional model of this solving the macroscopic equation. So the solver works like this. First, we solve the spectral cell problems to compute beta and nu plus. Then we solve the cell corrector problem, which requires actually these quantities. And we complete the effective dispersion. And then we write the results. It's a small file. The algorithm can also work on a structured and orthogonal grids, which is exactly what we do actually, because the geometry is, of course, complicated. The code is available here for free at GitHub. You can download it and use it. It works with OpenFOAM 7 at the moment. So these are the cell problem looks like. You see the eigenfunction, the adjoint function. They look very similar to what the concentration field will look like, but there is no decrease or increase depending on the sign of the reaction, of the concentration on the flow direction. This is the magnitude of the corrector, which looks weird, but if you look at the single components, actually looks pretty meaningful. And this is the effective velocity that looks more or less like the original velocity, a bit faster. So comparing against direct numerical simulation gives us very good feedback, I would say. Because it turns out that this method is very accurate, even in this situation where the scale separation is not so evident. So epsilon is not very small. And you can see there is some discrepancies, especially where the Damkohler number is very large. But it's also true that here the concentration is changing very quickly. So we also applied this method to a parametric study. So we studied a wide range of Damkohler numbers, packet numbers, and the porosities. And we also applied it to electric potentials. And so where you have an electric field that is driving your concentration because you have charged particles. And everything is in the publication I mentioned earlier. And I would say, yeah, from the point of view of reactive homogenization, that is what we've done so far, state of the art of what we've done. The other topic I would like to discuss about is the topic of conjugate transfer. Now, conjugate transfer is very similar actually to reactive transport. The difference is that now we are considering also what happens inside the grains. So also this one is based on a publication, a work we published earlier in the beginning of the year in physical review research. So this is our, let's say, sample sketch domain. See, we still have a region where there is a flow field, but then we also consider what happens inside the grains, which are called the mobile regions in this modeling community. Because there is no velocity field here, clearly, there is just diffusion inside the regions. And there are fluxes from one region to the other. So what happens is that these regions have some inertia. They absorb concentration, they release concentration. And so they have effects that are non-local in time, which should be taken into account. The objective is still the same. We want to find a macroscopic model. We don't need to solve it in an explicit way for these boundaries or for the exchange. So there are a lot of models for this kind of problem. The most famous one is probably the multi-rate mass transfer model of Algetti and Garliff. There are also integral differential formulations, continuous time random walk. It was demonstrated that they are all more or less similar. They cannot be reduced to a multi-rate mass transfer. The only issue is that it's not so clear how to determine closure coefficients. In porous media, often geometries are complicated and rely on fitting data. But for example, if someone wants to design an heat exchanger, then you know very well the geometry at the microscale. You know very well that this is a self-repeating geometry. So perhaps having a very formal way to evaluate the closure coefficients that is very useful clearly. Also the assumptions regarding how the fields in the mobile region affect actually the exchange. For example, the effect of advection, how advection can affect the exchange is not clear. So the question is it possible to derive a general model from first principles? And we answer this question introducing a formal way to upscale advection diffusion problem coupled with the diffusion problems. So we have an advection diffusion equation in the mobile region, more or less like before, but we also have diffusion equations in the immobile regions, in these grains. They are coupled through Neumann-Dirichlet coupling, which is a standard coupling, continuity of concentration and continuity of fluxes. The dimensionless group here is just the packet number, and the only condition is that the packet number is much smaller than 1 in the immobile regions. Here we will apply volume averaging. So this is what is called sometimes Favre integration kernel. Favre is a term that comes from compressible flows. It's been adopted in multi-phase flows. I'm using it here. It's basically volume averaging over the volume occupied by the particular phase. It's just another way of smoothing the fields. So if we apply volume averaging, we obtain the multi-continuum model. So these are this is the volume average equation for the mobile region. I don't care at the moment about the form of these fluxes. We can assume that they are given by all the analysis I've done before. For example, can be used to evaluate these fluxes here. What is important in this particular application is the exchange term, this m dot. So the problem is now is finding m dot, which is just the boundary integral. Classic volume averaging and boundary integrals come out. Again, we perform the same exact strategy, divide and conquer. We perform a linear decomposition. So C is split into psi and C prime. Psi will take the homogeneity of the boundary condition, solving now just a Laplace operator because there is no advection here. C prime instead is solving the remaining problem with an homogeneous boundary condition this time. And we can express C prime in a series of eigenfunctions. Now, since it's just diffusion, we have a self-adjoint problem, so we can just consider eigenfunctions. And they again satisfy the eigenvalue problem. And you see here that the value of the eigenfunction and the value of the eigenvalue are simply given by the geometry of the immobile region and the material properties, so the diffusion coefficient of the immobile region. So they don't depend in any way by the packet number, for example, in the mobile region, or by the fact that in the mobile region there can be reactions in the back. So now we can apply Duhamel's principle, and using variable separation is a stimulable problem. So we can use the classic techniques that we are using for heat transfer, and we get a set of ODEs in the end, exactly like in the multi-rate mass transfer model, the standard multi-rate mass transfer model of Conjugate and Gorelick, with the exception that we have this term here that is just a projection of this psi field over the eigenfunction scaled by a factor. Actually, this looks very similar to other kind of short video. So now let's focus on the mobile region. We saw before from a generalization theory that we can express the fields in the mobile region in asymptotic expansion. We do the same here. We assume that we can express in a series of correctors in this case. So this is similar to the corrector we saw before. Actually, it's basically the same thing. But the higher the order, the higher also the order of the corrector. So the corrector will be first order 10, so order 1, so vector, second order 10 order 2, and so on. Substituting this expression in the equation for psi gives us a similar expansion for psi and similar equation for psi. So we have these new correctors that are the correctors of psi, big psi. Upside. Plugging everything back, we get the generalized multi-rate transfer model, which is similar to the original multi-rate mass transfer model up to here. While here we have a correction term that depends on the inhomogeneity of the concentration field within the immobile region, within the mobile regions. Also in the mobile regions, we have some differences. The concentration relative to mode K for the mobile region I is actually exchanging with this equilibrium concentration, not necessarily with the average concentration. This is a reflection of the physical fact that the mobile regions are really not exchanging with the average concentration of the whole REV, but they are exchanging with a local concentration. So the improvement of this model is that we are trying to approximate the local concentration. And the fact that the average concentration and the local concentration may be different, this depends on the kind of transport that exists in the mobile region. So non-uniform boundary conditions do not affect the exchange rates, but instead they change the equilibrium concentration. So when you try to fit your data, if you cannot find a way to fit lambda, you may try to consider instead changing the exchanging concentration. So if we truncate at leading order, we get aggregate and Gorelick, which means that aggregate and Gorelick is a kind of homogeneous approximation. So we assume that when it comes to exchange between regions, the concentration in the mobile region is homogeneous. All over the REV, there is the same concentration equal to the average, and we get the same equations, the same parameters, which remains the same anyway, even at higher orders, because they don't depend on this kind of truncation. At the first order, we get an approximation we call drift flux, because the new term, other than the term here, there's a new term in the mobile region that can be considered as a drift flux, so an additional velocity. And the second order, which is quite rare because it's very difficult to find homogenization up to beyond the first order. And in this case, one can consider that this term looks a bit like an effective dispersion. So this can be a diffusive flux approximation. If you go higher orders, of course, we get higher derivatives, and the whole process may not be worth anymore. Again, we perform numerical, we use numerical methods to solve these equations, of course. We have a solver in open form, where the mobile region and the immobile regions are coupled implicitly, in a segregated way, but implicitly, let's say, through a loop, through a Picard iteration. So first we solve the equation for the mobile regions, then we apply the fields, then we calculate the source from the mobile regions. The mobile regions is solved, and then we continue until we converge, and then we go on to the next time step. So in this way, we show that the solution is accurate. We have a new paper that is not published yet. At the moment is an archive, preprint there. You can check it out. There is all the numerical implementation in open form of this. There is the library that we implemented, described in detail. There are a lot of numerical examples, also not necessarily from applications in geological flows. So we developed all of this in the CQ project. That's the knowledge at the end. And of course, it's available. The code is freely available from our repository. You can find it here. The only thing I want to show you about this numerical solution is that you can get some insight about how the multi-rate model works by running simple cases for which you have an analytical solution. In this case, this is the analytical trend. You see that based on the kind of material that you have, this omega is the response in time of the material. So the ratio between the diffusion coefficient of the immobile region and the square of the reference length. So you see the smaller, so these frequencies. So the faster the oscillations are, the faster the response time is, the more modes you need, because actually higher modes correspond to faster reactions. And yeah, we see that if you increase the number of modes, so here we use 400, it takes a lot of time to solve. You can match pretty well the kind of 3/2 profile. It's just porous medium that is unloading, so it's not a particularly complicated test case. It's also in the library. You can also run it. All right. Then to wrap up and conclude, I show that it's possible to obtain microscopic transfer models equation from first principles using a decomposition approach to isolate relevant physical phenomena. And this is the approach we use in these two situations. So another important take-home point is that the effective transfer rates do not depend on the properties of the mobile region, but the mobile regions only. And now we are working to extend this also to particular flows and to cases where you have a layer covering the mobile region, so you have kind of delayed response. Regarding the reactive transport, we're also extending that to dissolution problems. That's very important for shale gas applications, for example. So thank you, and open questions.
Okay, yeah, then thank you very much for that interesting talk. Yeah, are there any questions in Zoom or YouTube or here in PoreLab? Don't think so for the moment, but in case that there will be some questions at YouTube, I would just propose that we forward these questions then to you. And yeah. All right, yeah. Again, thank you very much. Very interesting, and yeah.
There are people there.
And yeah.
Right. Then I can stop sharing it. No, I'm new to this software. All right.